Hi everyone, my name is Ashley Bedford and welcome back to the Runtime Diaries. So today I am super excited to bring you day 6 problem, maximum product subarray. And this is with Educative's hashtag 30 days of code challenge. So I'm going to break it down for you here. Let's get into it. This challenge problem is all about moving from brute force repetition to identifying patterns and finally modeling your logic efficiently in just one pass. So let's restate the problem in plain English. We're given an array of integers, some positive, some negative, maybe even zeros, and we need to find the largest product we can get from multiplying a contiguous subarray. Contiguous just means the numbers have to be next to each other, no skipping around. And at the end, we only return that maximum product value, not the actual subarray. This sounds straightforward, right? But wait, negative numbers and zeros completely change the game here. Here's where most people get tripped up. First, multiplying two negatives gives a positive, so a bad streak might suddenly turn good. Second, if you hit a zero, your entire product chain resets. And third, if you try to multiply every possible combination manually, you'll end up repeating tons of work. That's the brute force of n squared approach. The key insight is realizing you don't have to start over each time. You just need to remember what happened at the last step. Let's start from that naive version anyway, because it's really useful as a baseline. In this version, we multiply every possible subarray and track the maximum. It works, but look what's happening here. We're recomputing overlapping products again and again. For the big input array, that becomes painfully slow of n squared time. There's no caching, no memory of what came before. So the question becomes, how can we carry forward useful information between steps instead of restarting the math every time? This is where the problem starts to click. At any index, one of three things can happen. If the number is positive, it naturally extends the previous product upward. If it's negative, it flips the sign. What was once your worst product might now become your best. And if it's zero, everything resets. You can think of it as a break in the chain. So instead of tracking just one running product, we track two. The maximum product so far and the minimum product so far, because that minimum might one day flip into your new maximum. This brings us to our core rule, or what's called the invariant. After processing index k, I always know the best and worst product values of any subarray that ends at that position. That means when I move to the next index, I don't need to go back or re-multiply. I just extend from the information I already have. The global maximum product is simply the largest best so far value across the entire array. Let's walk through it visually with the example input from left to right, 2, 3, -2, 4. At index 0, the best and worst are both 2. At index 1, multiply by 3. The best equals 6 and the worst equals 3. At index 2, we hit a -2. A negative flips everything. Our best drops to -2, but our worst becomes -12. Then at index 3, multiply 4 times -12, which equals -48. That stays negative, so our global maximum remains 6. By tracking both paths, we never lose sight of a potential comeback when signs flip. Now that we understand the pattern, here's the O of n optimized solution. We initialize the first value as both our best and worst ending products, as well as the global max. For each new number, we store the previous best and worst. If the number is negative, we swap them, because multiplying by a negative flips their roles. Then we compute new best and worst endings and update the global max. That's it. One loop, no nested calculations, constant memory. In this version, our runtime is O of n, just one sweep through the array. Space complexity is O of 1 because we only use a few running variables. We eliminated repeated work, handled zeros and negatives naturally, and maintained a clean single-pass logic. No extra arrays, no division, and no brute force. This problem is such a great teacher for algorithmic thinking. The big takeaway here? Always ask yourself, am I doing the same work more than once? Then, identify what information you can carry forward. In this case, remembering both extremes, the best and the worst, turned a messy O of n squared approach into a beautiful O of n1. Before we wrap up, try this twist on your own. What if the array contained fractions or decimals, meaning numbers between 0 and 1? Also, would multiplying them change your logic or just your thresholds? This question pushes you to think beyond integers about how scale and magnitude interact. And that's day 6. Thank you so much for joining us for the hashtag 30 Days of Code Challenge with Educative. We're going to be bringing one problem every single day. So we're going to solve it for you, break it down. You're going to learn so much from this upskilling journey. If you like it, share it, subscribe, and we'll see you tomorrow.